The Distributed Ledger Synchronization Protocol, referred to throughout this documentation as DLSP, defines the operational framework for maintaining consistency across geographically dispersed ledger nodes. This protocol establishes a deterministic ordering mechanism for transaction propagation and settlement validation. The specification assumes a network topology composed of at least 3 independent validating nodes, each maintaining an identical copy of the canonical ledger state. Nodes communicate via standardized message framing over TCP connections with configurable keep-alive intervals. Transaction submission enters the protocol at the ingestion layer, where client requests are first assigned a monotonically increasing sequence identifier. This identifier is generated locally on the receiving node without internode coordination. The transaction payload, including sender identity, recipient reference, and value transfer amount, is encoded in protocol buffer format for wire transmission. Encoding adds a 4-byte checksum field computed via CRC32 polynomial. The transaction is then queued in the pending transaction pool with a timestamp marking local system time. The pending transaction pool maintains transactions in submission order until broadcast consensus is achieved. The pool has a maximum capacity of 8,000 transactions. When capacity approaches 90%, older transactions exceeding a time-to-live threshold of 300 seconds are automatically removed. Transactions below this age threshold are retained regardless of pool saturation. The eviction process operates independently on each node and may result in temporary divergence between node pools before synchronization occurs. Consensus rounds initiate on a fixed time-based schedule occurring every 5 seconds across all validating nodes. At round initiation, each node constructs a proposal containing up to 1,000 transactions selected from its pending pool in chronological order. The proposal is serialized with a round number field, node identifier, and cryptographic signature, computed using EXA over the SHA-256 hash of the proposal contents. Proposals are then multicast to all peer nodes within the network. Upon receiving a proposal from a peer node, the recipient node validates the proposal structure and cryptographic signature. Signature verification fails if the round number is older than the current consensus round -10, or if the signature does not match the declared sender node identity. Failed validations trigger discard without further processing. Valid proposals are stored temporarily in a proposal buffer organized by sender node identifier and round number. The buffer maintains a maximum of 100 proposals per node before older entries are evicted. Transaction inclusion requires approval from a quorum consisting of at least 2 validating nodes. When a node receives proposals from all peer nodes for a given round, it compares the transaction sets and identifies transactions appearing in at least 2 proposals. These duplicated transactions are marked for commitment. Transactions appearing in only a single proposal remain in pending state and are reconsidered in subsequent rounds. The quorum requirement ensures that no single node can unilaterally introduce transactions into the canonical ledger. Committed transactions are appended to the canonical ledger in a deterministic order derived from round number and transaction sequence identifier. Each ledger entry contains the transaction data, round number, and a ledger offset value representing its absolute position. The offset begins at 0 for the genesis ledger state and increments by 1 for each subsequent entry. Ledger entries are immutable once written. The ledger is persisted to disk after each consensus round completes, using a simple sequential write pattern to an append-only file. State accounts are maintained in a sorted key value store indexed by account identifier. Each account record contains a balance field, non-C field, and timestamp of last modification. Transactions transfer value between accounts by decrementing the sender balance and incrementing the recipient balance. The non-C field increments with each transaction originating from that account and prevents replay attacks. Balance modifications are atomic operations requiring the entire account record to be rewritten to the persistent store immediately following ledger commitment. Node synchronization occurs when a node detects a ledger offset divergence with peer nodes. Divergence detection happens through periodic state queries sent to all peers, requesting their current ledger length and root hash of the ledger contents. If local ledger length is less than peer length, the node enters catch-up mode and requests missing transactions from that peer. Missing transactions are requested in sequential batches of 500 entries starting from the local ledger length plus 1. Catch-up transactions are validated individually before integration into the local ledger. Validation includes verification that the transaction sender account held sufficient balance at the time of transaction processing, and that the transaction on scene matches the expected sequence number for that account. Validation failures indicate data corruption or Byzantine node behavior and trigger immediate network alerts. The node discards the corrupted transaction batch and queries alternative peers for the same ledger range. Network partitioning occurs when node groups become unable to communicate due to link failures. The protocol handles partitions through partition tolerance mechanisms. Minority partitions, defined as containing fewer than 2 validating nodes, cease consensus processing and enter standby mode. Transactions submitted to minority nodes are queued but not committed. When partition healing occurs and communication is restored, minority nodes discard their queued transactions and synchronize to the majority partition state. Byzantine fault tolerance in the protocol assumes at most one validating node can behave maliciously per consensus round. With 3 nodes, one node can be Byzantine and the protocol continues to achieve safety. A Byzantine node may submit fraudulent proposals containing invalid transactions, duplicate transactions, or transactions with insufficient sender balance. The quorum requirement ensures that transactions from Byzantine proposals cannot be committed unless at least one honest node also proposes the same transaction. Clock synchronization across nodes is achieved through a simple algorithm applied at the start of each consensus round. Each node records the local system time and the median time from all received peer heartbeat messages sent in the previous round. If the local time differs from the median by more than 5 seconds, the node adjusts its system clock forward or backward to match the median. This creates a bounded clock skew across the network of at most 5 seconds in either direction. Ledger pruning operations remove historical transactions older than a configurable retention period, defaulting to 365 days. Pruning is performed offline and requires the target node to be temporarily unavailable for consensus participation. The pruning process reads the ledger sequentially, identifies transactions exceeding the age threshold, and writes a new pruned ledger file. State account records are recomputed from the genesis block to the pruning boundary to ensure correctness. Upon completion, the old ledger file is retained as an archive. Configuration parameters for the protocol are stored in a YAML-formatted configuration file read at node startup. Key parameters include the consensus round interval in milliseconds, the transaction pool maximum capacity, the Byzantine fault tolerance threshold, and the clock synchronization maximum skew value. Changes to configuration parameters require node restart and do not take effect dynamically. Configuration files are versioned and previous versions are retained in a configuration history directory for audit purposes. Operational monitoring of DLSP deployments involves continuous collection of ledger growth rate, consensus round completion times, and network message latency metrics. These metrics are aggregated on a per-node basis and reported via standard syslog output. Alert thresholds are defined for anomalous conditions including rounds exceeding 30 seconds to complete, account balance inconsistencies between nodes, and Byzantine node detection. No immediate automatic remediation occurs. Alerts are logged and may trigger manual operator investigation according to deployment procedures.